Good morning, everyone. So today we will start the day off with Gary Shiu from Wisconsin. So he will be telling us about formulating the weak gravity conjecture in AdS space. Please.
Okay. So thank you very much for having me here. It's always a pleasure coming to Korea. So I will be talking about the weak gravity conjecture in AdS space. Some of you who were in elementary school when the weak gravity conjecture was proposed may ask, what else can we possibly learn? Isn't this ancient history? It has been almost 20 years since the weak gravity conjecture was first formulated. And I like this plot from Inspire, which shows the ups and downs. So the paper was a sleeping beauty for several years, reaching its low point in 2013. And it regained its momentum sharply around 2014, thanks to BICEP2. And then COVID hit. Since then, the weak gravity conjecture has been showing a downward trend. Okay? Either because we are busy trying to stay alive, or because many consider this to be a done deal. Okay? So how do we make the weak gravity conjecture great again? Okay. The weak gravity conjecture is actually a misnomer because it's not a single conjecture, but rather a conglomeration of related conjectures of quantum gravity. I will review the motivations behind some of these conjectures in this talk. But despite these many variants, the weak gravity conjecture has mostly been formulated in asymptotically flat space. Okay? This can be understood because stronger versions of the weak gravity conjecture, such as the Tower weak gravity conjecture, and relatedly, the emergent string conjecture put forth by Sunju and collaborators, requires knowledge of the UV completion and not just the low energy supergravity. In its simplest form, the weak gravity conjecture demands that an extremal black hole must be able to decay. And in a paper with my student Pusen Lin last year, we computed the Stringer rate for Rising-Ostrom black hole in order to determine the dynamical criteria for extremal black hole to decay. So part of the motivation is to gear up for subsequent work with also Alessandro Menino to identify what might be the weak gravity conjecture for AdS. Okay? Now, we find some interesting subtleties, which I would explain in this talk, and we'll leave the de Sitter case for the future. Now, yesterday, Tarek and Christian independently invited the younger folks here to join the effort to solve de Sitter quantum gravity. So I would just add this problem to the list. Okay, so why are we interested in the weak gravity conjecture in AdS space? The weak gravity conjecture is usually stated as the requirement that extremal black holes can decay without running into a naked singularity, or alternatively, there exists a self-repulsive particle. Now, the borderline case for the first formulation is when there are symmetries protecting the black holes from decay. For example, BPS black holes saturates the weak gravity bound in asymptotically flat space. However, BPS, at least electrically charged black holes in AdS, were known to have naked singularities. So demanding extremal black holes to decay without naked singularity seems, the motivation behind seems kind of moot. Furthermore, the cosmological constant give rise to in AdS give rise to a confining potential. So the second formulation also doesn't look right because no particles emitted by the black hole would be able to escape indefinitely. So there are two simple consequences due to this confining potential. There's no simple kinematic criterion on the particle spectrum in order for extremal black hole to decay, unlike the asymptotically flat space case. And furthermore, no particles can escape, can self-repel indefinitely. So which of the criteria, one or two, if any, is the correct generalizations of the weak gravity conjecture in AdS space? Now, another motivation for studying the weak gravity conjecture in AdS is holography. So some of the statements that we made with black holes in AdS should be translated to properties of the dual CFT. So in order to compare with the AdS case of interest, let me review some versions of the weak gravity conjecture, starting from its precursor, namely the absence of global symmetry. The conjecture is that global symmetry, exact global symmetry does not exist in quantum gravity, that Shiu also mentioned yesterday. Now, it has been conjectured long ago that global symmetries cannot be exact in quantum gravity. There are many arguments for that. So, for instance, there is a proof in perturbative string theory that any continuous symmetries must be gauged. And you could also see why this is the case by thinking about black holes. Now, the Hawking radiation of a black hole is insensitive to the global charge it carries. So you could imagine throwing matter field with global charge into the black holes. And now you have these different black holes with different global charges. As you wait sufficiently long, they Hawking radiate. So eventually, you will end up with infinitely many indistinguishable black holes within a finite mass range. And this is thermodynamically problematic. That was the argument also mentioned by Shiu yesterday. Indeed, in perturbative string theory, you can show that anytime when you see a global symmetry, you must be able to find the corresponding gauge bosons for that. So the symmetries, continuous one at least, are gauged. And the absence of global symmetry has also been revisited in light of AdS CFT without reference to the world sheet. Okay? Now, there are many phenomenological implications of this no global symmetry conjecture. For example, you can show that if there's no global symmetries, if you find that there is a dark matter particle that carries a tiny irrational electric charge, there must necessarily be a massless dark photon. Okay? So the argument is basically that if you can find this global symmetry, if you can find these dark matter particles carry this irrational charge, you can construct operators that involve only the dark matter field and only the standard model field. And as a result, there's a global symmetry acting on only one of the sectors, which, as we argue, cannot exist. So there must be a gauge bosons associated with that symmetries. So the weak gravity conjecture can be thought of as an upgrade of that statement. Since global symmetries can be thought of as gauge symmetries with a vanishingly small gauge coupling, it's natural to suspect that problems would arise when the coupling becomes too weak. So the question is, when do things go wrong? At what value of the coupling will things start to go wrong, and how? Okay? So the weak gravity conjecture is, in its original form, was stated as the requirement that any non-supersymmetric extremal black hole must be able to decay. Otherwise, you would have infinitely many stable states with this carrying this charge. Although, unlike the global symmetry case, these infinitely many stable black holes have increasing mass. So you have only a finite number of them below a certain mass scale. So there is no remnant problem here, a priori. That's the reason why this is still considered as a conjecture. Seems to be problematic having all these infinitely many stable states labeled with the charges around, although you cannot make the argument as precise as in the global symmetry case. Now, for extremal black holes, the Hawking temperature is 0. So the black hole can decay by shedding off its charge. And this is the process that we are going to compute here in this talk. Without doing anything, you can already see that the resulting black hole after the emission of the charged particle must be sub-extremal. Otherwise, there would be a naked singularity already for this gravitational solution. In asymptotically flat space, the particles that is emitted from the black hole can be infinitely separated from the black hole. And when they are infinitely far apart, there's no need to consider binding energy. And therefore, kinematic considerations alone already tells you that these particles that lead to the black hole decay must be super extremal with charge bigger than its mass. Now, the conjecture only requires the black hole to decay. You don't need every single state in the theory to satisfy this inequality. You just need to find at least one state with charge that is super extremal, with charge to mass ratio bigger than that of an extremal black hole. So this is one way to state the weak gravity conjecture. Another way to state the weak gravity conjecture is that there must exist a state on which gravity acts as the weakest force. Now, again, this does not imply that gravity is the weakest force for every state in the theory. There must exist a state in which gravity is the weakest. It also does not mean that gravity is the weakest force at all scales, at all energy scales. So the gravitational couplings runs faster with energy than the gauge coupling. So if you go to high enough energy, the gravitational coupling eventually will catch up. And does that mean that the weak gravity conjecture will be violated at sufficiently high energy scale when the gravitational couplings become large? Well, this does not happen because you can run the same argument as the weak gravity conjecture, not for electrically charged objects, but for magnetically charged objects. So imagine you have a magnetic, if you demand a magnetic extremal black hole to decay, the same argument that I gave earlier would imply that the charge to mass ratio must be bigger than that of some extremal one. Okay? So now for magnetic monopole, the magnetic charge goes like inverse of the coupling, and the mass goes like also inverse with the coupling, but with the UV scale that sets the mass of this monopole. As a result, the UV cutoff scale implied by the magnetic version of the weak gravity conjecture tells you that the cutoff scale is parametrically below the Planck scale. Okay? So at weak coupling, this is a much lower energy scale. Before you hit the Planck scale, your description already breaks down. So way before you hit the scale at which gravitational coupling becomes strong, you should no longer be trusting your theory. So there's no contradiction. So therefore, it has been conjectured that there must exist some self-repulsive particle in the same way that the black hole decay argument seems to suggest. So there must exist at least one self-repulsive particle on which gravity still acts as the weakest force. But it has been known for quite some time that in the presence of some additional master scalar fields, the requirement for black hole decay and in particular, the extremality bound that I stated earlier, and the repulsive cost conditions do not need to match. Okay? However, there's evidence that both seems to be satisfied in the examples that we can check. So that seems to be true whether you want the weak gravity conjecture to be super extremal particles or self-repulsive particles, the statement seems to be satisfied. These two statements seem to be satisfied in any consistent theories that we could check. Like string theory models, yeah. So so for most of us, that would be string theory constructions. Right? In fact, many of the strongman arguments is either a combinations of black hole arguments, which I was presenting, or explicit checks with string constructions. So for instance, Sundru is a world expert in his business, checking many of this tower conjecture and emergent string conjecture. Okay, so the argument that I gave earlier for the weak gravity conjecture was for one-form gauge symmetries. You can generalize these arguments for any p-form, higher form symmetries. The difference is that the higher form symmetries couple to extended objects rather than particles. So you could ask, what would be the requirement for some extremal, for some branes in a consistent quantum theory of gravity, whether the charge to tension ratio is bigger than that of the extremal branes. Now you can of course do that for higher form symmetries, but it turns out that it's a lot more interesting to ask the questions not about higher value of P, but go lower values in P. In particular, an axion is a zero form gauge field. The charged objects under the axions are -1 branes, which are the instantons. So if some form of the weak gravity conjecture holds for even -1 form symmetry, there must exist a -1 form object whose charge to tension ratio in some way is bigger than some well-defined bound. Okay? Now, what translates from tension for a p-brane would become the instanton action, and what replaces the charge will be inverse of the axion decay constant. After all, the inverse of the axion decay constant determines the coupling of the axions to these instantons. Okay? But it is a lot more tricky in regards to the -1 form symmetry, because there's no clear notion of extremality for instantons. There's no notion of decay. So what are we talking about here? So it turns out some arguments can be made, although it's not bulletproof, that there seems to be a generalization of the weak gravity conjecture to -1 form symmetries as well. And what sets the order one factor here instead of the extremal object, it's replaced by a Euclidean wormhole. Okay? So this statement is not at all that obvious because there are many gravitational instanton solutions. There are core instantons that are singular. There are extremal instantons. For instance, D instanton would be one of them. And then there are Euclidean wormholes. They have different charge to action ratio. And so we find some evidence that the bound should be set by that of the Euclidean wormholes. And why is the axion version of the weak gravity conjecture interesting? Well, the decay constant tells us the range of the axion field. So typically, the axion potential is periodic with periodicity equals to 2 pi times f. And that axion decay constant determines the range of the axion field. And this is also what sets the amplitude of gravitational waves generated by axion models of inflation. So if you were to bound the axion decay constant to be sub-Planckian, that tells you that you could not get a viable model of axion inflationary model. Okay. Now, there are many stronger versions of the weak gravity conjecture. For instance, if you have more than one U1s, black hole decays would require that there must exist a super extremal particles that is charged under each of the U1 gauge field minimally. So if you don't have that, then a singly charged black hole will not be able to decay in the respective directions. But that's not enough because there could be multi-charged black holes that still cannot decay if you only have super extremal particles charged under each of these directions. So it turns out there's a simple mathematical statements you can make for multiple U1 case, and that is the convex hull generated by the charge to mass vectors of states in the theory should be big enough to contain this extremal ball. If you are in a situations like this, where so these are the charge to mass vectors. In this case, there are two U1 directions. So having super extremal particles charged under each of these U1 directions is not enough to guarantee that a black hole with a charge like this can decay. And the requirement for every charged black hole to be able to decay is that the convex hull is big enough to contain the entire black hole region. Okay? To see how this convex hull condition comes about, you can consider the decay of a black hole with a total charge Q and mass m into its constituents, consisting of particles with different species. And for charge conservation implies that the charge of the black hole equals to the sum of charges of these constituents. And energy conservation implies that the total mass of the constituents should be smaller than that of the black hole. And so you can work out that in order for these conditions to be satisfied, the charge to mass vectors of the black hole should be a subunitary weighted average of the charge to mass vectors of the constituents. And so this is where the convex hull conditions come out. Okay, now you could, so consistencies with dimensional reductions suggest even further upgrades. You could consider compactifying the theory on a circle, if there's a circle. And there is a new one that was already present before the compactification, and you also generate an additional U1, namely the KKU1. And so now you could check whether the convex hull generated by the charge to mass vectors of the states in the theory is big enough to contain the extremal ball. And since the KK states are BPS, for sufficiently small radius, you find that the convex hull does not necessarily contain the extremal ball. And this motivates a stronger version of the weak gravity conjecture, known as the Tower weak gravity conjecture. And that requires infinitely many super extremal or extremal states that generate a big enough convex hull to contain the black hole regions. Okay? Okay, so with this quick review, we could now ask the question, what would be the weak gravity conjecture in AdS space? So the first question that came to mind is the black hole extremality bound. Okay, so unlike asymptotically flat space, the relations of mass and charge of an extremal black hole in AdS is no longer linear. And here, I give you the extremal black hole solutions in AdS for Einstein Maxwell theory. R is the radius of the black hole, L is the AdS length. And for large extremal black holes in AdS, the mass of an extremal black hole actually goes like its charge to the power of 3/2. And the linear relations between the mass and charge is only reproduced for the flat space linear relation is only reproduced for very small black holes. Okay, in particular, if you consider an uber large extremal black holes where all the higher derivative corrections can be ignored, you don't have to go to anything beyond Einstein gravity. In that case, the charge to mass ratio of an extremal black hole goes to 0. So in other words, the extremal bound does not seem to give you any non-trivial constraints on the particle spectrum in order for the black hole to decay. So in other words, the extremal bound is not what we are looking for the weak gravity conjecture in AdS. Now, because of the confining potential, you cannot simply deduce the mass of the particles from that of the black holes. So remember, I gave you this argument that when you have black holes in asymptotically flat space, when the particle is infinitely far away, there's no binding energy, so you can just use kinematics to deduce what's the mass of the particles that is emitted in order for this decay to be possible. Here, the confining potential does not let you do that. And consider a particle in AdS Rice-Nordstrom background. And for particles that are far away from the black hole when R is large, the confining potential dominates. So the force experienced by the particle is always attractive. That means that the particles cannot escape. So you cannot ignore the binding energy in deducing the mass of the remaining black hole. The repulsive force condition is also suspect because the particles cannot escape to infinity. So what we're talking about as far as self-repulsive particle goes. So what is the right generalizations of the weak gravity statement in AdS? So this question motivated us to compute the Stringer effect of Rice-Nordstrom black holes. Okay? So this is a cartoon of different limits you could consider. So when the Compton wavelength of the particle emitted by the black hole is small, compared with the size of the black hole, the production rate is exponentially suppressed, as you expected from Stringer effect. It's exponentially suppressed process. However, when the Compton wavelength of the particle is comparable or larger than the size of the black hole, you have unsuppressed charge condensation. So as a matter of how the mass of the particle compares with the mass of the black hole, you have two different limits. Okay? So this is the dynamical process for black hole decay, at least the picture on the left. We first compute the Stringer rate for a flat space Rice-Nordstrom black hole in its full geometry. And our computation suggests that the Stringer rate, here we are interested in the local Stringer rate, so how rapidly this production happens at different distances from the black hole. And we find that our results tell us how the Stringer rate falls off with distances from the black hole. Moreover, we show that this decay rate approaches 0 when the charge to mass ratio of the particles approaches 1, as the weak gravity conjecture suggests. So if you start out with a particle with a charge to mass ratio bigger than 1, this decay process is possible. And when you approach an extremal particles, this effect shuts off. And when you go below that, this would not be a real quantity. That means that this is not a decay process. Okay, so that was the results for flat space. And in a subsequent paper, we generalize our computations to AdS space. And we find that the critical value of the charge to mass ratio for the black hole decay to be possible is enhanced by this factor. So where eta is the black hole in AdS units. Okay, so this criterion comes from analyzing the existence of well-lined instantons that contributes to the Stringer process. Okay. And yeah. Yeah, okay, so I would explain it later on. So this is the well-lined instanton actions for AdS2 cross S2 geometry. And so maybe it's a good time to actually say a few words about this expression. We are considering the string array at different places. And since much of the string array process happened near the horizon of the black hole, to leading order, the string array effect should be determined by the well-aligned instanton actions for the AdS 2 cross S2 geometry. This is the corrections that we compute. So we know exactly how fast it drops with distances. So as you go away from the near horizon region, there is a fall off of the effect. And this fall off distance scales is the Compton wavelength of the particle. So, and it tells if it was not because the full black hole geometry changes the, so the near horizon symmetry is AdS 2 cross S2. If this symmetry is exact, then you will actually have a divergent factor. That is because the volume is infinite. And because the black hole solutions break that near horizon symmetry, so there is a fall off behavior, and the final string array is actually finite, integrable and finite. Okay, so, but I haven't told you how we compute that. It will come next. In any case, for AdS, that answer is modified by the size of the black hole. And these conditions come from whether well-aligned instantons that contribute to the string array process exist. And besides computing this effect directly, we gave evidence that this is the right form of the weak gravity conjecture in AdS by comparing this condition with a notion of a repulsive force condition that I will state more clearly, and the near horizon BF bound. So there are three different ways to state the results. One is whether the string array process is possible, string array is non-zero. There's some form of repulsive force conditions, but not when the particles are infinitely apart. And there is also a criterion that you can write down based on the near horizon stability. And that's three conditions turn out to be equivalent. Okay. But then if you are quick, you may immediately see that there may be a potential contradiction, right? And that is because if the weak gravity conjecture is a statement that all extremal black hole must be able to decay, you should extremize the right-hand side for the strongest conditions possible. And the strongest condition comes from the largest black hole that you can possibly write down. And that gives you a condition that the charge to mass ratio is bigger than √2. And you can actually work out for general d dimension, it's a factor bigger than 1. It's a d-dimensional factor. Now, in theories with extended supersymmetry, every state satisfies the BPS bound. So isn't the BPS bound the charge to mass ratio smaller than 1? So there seems to be a contradiction between this weak gravity condition that we wrote down and the BPS condition that needs to be satisfied in extended supersymmetric theory. So what's going on? I'll come back to it later on after I show you the results. But it's also quite interesting to try to test this conjecture with explicit complexifications of string theory. In flat space, it's exactly saturated. So the BPS bound is opposite to the weak gravity bound, but then the BPS state saturates the bounds. So in the case of flat space, the BPS state saturates the lower bound.
I was always confused by this
statement
because electron is
yeah.
charged.
Yeah.
Some hypothetical string theory broken activity.
Yeah.
It's well below or super extreme.
That's okay. Yeah.
Is that right?
Yeah. Yeah. So it satisfied the bound, right? But then.
Yeah. I mean, what's confusing me is sort of the BPS bound itself.
Yeah.
If you take it seriously, electron shouldn't exist. On the other hand, we have conjecture below electron. But
the answer would be that in the electron exists, but then we are not living in a supersymmetric world. So the BPS bound does not apply to theories with broken supersymmetry. But the weak gravity conjecture is supposed to hold even for supersymmetric black holes.
I mean, what if your supersymmetry was broken at 1 keV?
That would have been okay.
1 keV replaced the electron.
Yeah.
And same question. I'm completely confused.
Okay.
Okay.
Okay. But in any case, so you only need one state to satisfy the conjecture. The BPS states themselves satisfies the conjecture. So there was no clear contradiction for flat space. But now that we enhance the weak gravity bound by a factor that is bigger than 1, so in extended supersymmetric theories, if every state satisfies the BPS bound, then you don't have any states that could satisfy this condition. So what's going on? Turns out there's no contradiction, but I'll keep you in suspense for 20 minutes until the end. Okay. All right, so let me just sketch what we did in this computation. So we compute the Stringer effect of Bryson Nordstrom black hole. Now, even though the Stringer effect was computed back in the 1950s by Stringer for a constant electric field, this computation, to the best of our knowledge, has not been attempted before. And the reason is, for the problems at hand, in order to calculate the local Stringer rate, we need to take into account the spatial profile of the electric field and the metric. It's not constant anymore. So how does the Stringer rate changes with distances away from the black hole? That's the questions that we're asking. Okay? But so the charged particle production is given by the charged particle production rate is given by the imaginary part of some effective action, which is associated with the vacuum transition amplitude in the presence of an electric field. So that was the Stringer calculation. And so the effective action is a sum over all the charge fields. You can consider the charge fields could be bosonic or fermionic. And for illustrations, we consider a complex scalar field charged under that U1. Now, the effective action that determines the rate of charge production is a sum over all the one-loop diagrams with arbitrary number of photons. And so this Stringer rate is non-perturbative in the electric coupling. So when we evaluate the path integral over the complex scalar, we can express this in terms of a functional determinant. And using the usual trick, you can write this effective action as an integral over some Stringer time of some propagator. Okay? Now, a common way to evaluate an effective action like that is the so-called heat kernel method, which is to trace over the eigenbases of the operators here that I call the Hamiltonian. This is the method that Ashok Sen used in computing corrections to the black hole entropy. Now, the heat kernel methods require knowledge of all the eigenstates, which is very difficult to obtain, except for problems with symmetries. So that was doable for the computations of corrections to the black hole entropy for extremal black holes because of the near horizon AdS2 cross S2 symmetry. Here, we are interested in the local Stringer rate, which requires us to go beyond the near horizon region. So that does not really work. So we opt for another approach, which is known as the world line formalism. And so the trick is to rewrite this kernel as a quantum mechanical position space integral over all paths connecting x and y. And in the end, you set x equal to y. And the world line is parameterized by the proper time tau. And the Stringer parameter is the total proper time. Okay? Now, if you work this out, you find that there are UV divergences of this path integral. The UV divergences come from the small s region, which fortunately is manifestly regulated by the kinetic term of the world line action. Okay, so whether you want to use the world line formalism or the heat kernel mechanism, there are UV divergences and infrared divergences that you need to treat with care. The UV divergence is related to renormalization of the couplings, which, as we have seen in the world line approach, is taken care of by this kinetic term in the path integral. There are two types of infrared divergences. So these Hamiltonian operators can have zero modes. And the zero modes would lead to infrared divergences in the large S region. Okay? Now, this zero modes comes from the near horizon AdS2 cross S2 symmetry. And if the geometry is exactly AdS2 cross S2, because of the constant curvature, everywhere in space would be equivalent. And that gives you an overall volume factor, which is infinite. That's the source of the infrared divergence. But the full black hole solutions break that AdS2 cross S2 symmetry. You do not expect to see this infrared divergence to appear. But then there's another infrared divergence which is of interest, and that comes from the Stringer effect that we are going after. The Stringer effect comes from the negative modes of the effective action. And that negative mode leads to an imaginary part of the actions, which signals the instability. So this is actually the good infrared divergence that we're after. And so we should be careful in counting the number of negative modes. And we find in this case, there is exactly one negative mode, which turned the effective action into a purely imaginary number. Yes?
This is also present in the original computation of the probability density.
Yeah, exactly. Yes, exactly. Exactly. Yeah. Right.
I mean, still computing the local
Yeah.
probability density.
Yes. Right.
That's perfectly fine.
Yes. Right. So, but we cannot make the assumption that it is everywhere the same. Right. So you would like to take into account the profile. But yes. So instead of energy density would take care of this infrared divergence. Right.
By the way.
Yeah.
So this computation is new, but along the same lines, I think there is some effort previously in the Turner effect AdS
Yeah.
some not.
Yeah. Right. Yes. Right. Right. So I think for us, the question is specifically for the black hole background. So everything varies with space. We want to know exactly how it varies. Okay. So in order to compute the Stringer rate, we would evaluate this path integral using stationary point approximation. So we first look for the stationary point, and then we analyze the quadratic fluctuations, including negative modes. And that's part of the tough part of the calculation is to exactly count the negative modes. Okay, so maybe I won't go into too much of the details, except to say that, well, there are many options to evaluate this saddle point. You could try to first integrate over the Stringer parameter, or you can first integrate over the instanton path, but both are giving you trouble. And the reason is, if you were to evaluate first over the Stringer parameter, you find that the resulting actions for the instanton path is non-local. And so if you are working with a non-local action, it's very hard to deal with the quadratic one-loop determinant of the quadratic fluctuations around it. So that's a no-go for us. And you could also try to integrate over the instanton path and then integrate over the Stringer parameter. But then this step is difficult in practice because you don't get an analytic answer in the first integral. And so what we did is to look for stationary points in the full space and analyze the spectrum of quadratic fluctuations. So in the process, we will compute both the instanton actions and the one-loop prefactor. Okay, so here are the stationary points that we find. And the second equation, you could recognize this as the geodesic equation for a charged particle in a Euclidean Rising-Nordstrom background. And for that reason, these solutions are known as well-aligned instantons. Okay, and here we are trying to look for what dominates the path integral. And so you could consider particles with angular momentum, but that's going to suppress the effect even more. So the dominant contributions come from solutions with zero angular momentum. And so the well-aligned instantons in the black hole background is they are given by spirals. Okay, and this is because in Euclidean signatures, all the coordinates are space-like, and so the gauge field is magnetic-like. So that's why they are going in circles, just like particles in a magnetic field, although this is in Euclidean space. So the instanton that contributes to the effective actions, they have the same beginning and end points, which translates to these instantons having self-intersection points. However, in general, these spirals do not close. They close only in the special case in the near horizon AdS2 cross S2 regions, where they become circle. So as you get closer to the black hole region, this spiral, as you get closer and closer to the horizon, these spirals will turn into circles. And precisely in this limit, you have analytic results because of the strong symmetry, the AdS2 cross S2 symmetries that you have. Okay, so now after we figure out what's the instanton actions that determines the exponential effect, this next is to determine the quadratic fluctuations, the one-loop determinant of the Hessian. I would not belabor you with the details. My student Pusin did an incredible job in doing this. And so we count the number of negative modes as precisely 1. But to compute precisely this one-loop determinant will require more care because they are formally divergent. So if you take the determinant of this matrix, it would have infinitely many modes and it's infinite. So you could regulate it with some reference operator. The end result is that when you put everything together, this is a Stringer rate that determines the extremal black hole decay. Now, to the best of our knowledge, nobody has computed this for the system before. Subsequently, there was an interesting paper by the Berkeley group in which they studied black hole decay using JT gravity. And so there are some differences between what we find and what they study. And the reason is that they, first, they did not try to compute this prefactor. So they could not see when the Stringer rate shuts off. And here we see that it shuts off when the weak gravity bound is saturated. When C is equal to 1, then this effect becomes 0. And secondly, they restrict the study to the near horizon region using AdS2 plus S2 symmetry. So they do not see how fast this Stringer rate drops off with distance from the black hole. Okay, so we could unpack this formula and understand each of the terms that contribute. Yes?
Oh, yeah, it looks like you're going to talk about
Yes, 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 very good. So, so the first thing you notice is to leading order, the Stringer rate is given by the near horizon AdS2 cross S2 answer. So you could evaluate that instanton actions with the circular instanton path, and that would give you the leading result. This is also expected because you are doing a Stringer calculation is suppressed by the action. Because we look at the detailed profile of how the metric and the gauge field varies with distances from the black hole. We also know the fall-off scale for the Stringer effect. It goes like the Compton wavelength of the particles that you emitted, which is expected. Now, the Stringer rate shuts off when the charge to mass ratio approaches 1, consistent with the weak gravity conjecture. And your question would be that why is that a divergent answer, right? So this is a divergent answer because when you approach the horizon, there is a restoration of the AdS2 conformal symmetry. And so there's an infinite volume again. But we know that this is an integrable effect. So even though naively there's a divergence, it doesn't give you an integrated divergent answer. And that is because away from the horizon, that symmetry is broken. And so the zero modes are lifted. So I don't think they go into this even in detail. Right? Because, I mean, yeah. Right. Yes. In principle, yes. Although I think they are going after this exponent mostly. Okay. So with that, we could go further and generalize it to AdS. And so the critical value, as I mentioned, for the Stringer effects to be non-zero is now modified by a factor that depends on the black hole size in AdS unit. Okay. So the first observation you could make is that the Stringer bound and the black hole extremality bound are different. So the extremality bound becomes smaller than 1 in AdS. In fact, it goes to 0 for the largest black hole. The charge to mass ratio of an extremal black hole in AdS goes to 0. Whereas the Stringer bound is stronger, it's bigger than 1. And this can be understood heuristically, why the Stringer bound is stronger than the extremality bound. And the reason is that the kinematic argument I gave in the beginning, that extremal particles lead to black hole decay, does not work for AdS. So the particle has to work against the confining potential in order for the decay to occur. So that's why this condition is stronger than that of the flat space result. And there is also, because of the confining potential, there is no clear notion of repulsive force in the sense of the repulsive force condition. So what exactly should be the right statement to make about repulsive force? Now, since we are considering black hole decay, a repulsive force on a charged particle near the black hole's horizon seems to be a reasonable necessary condition. So we call this the near horizon repulsive force condition. And there's a weaker condition than the repulsive force conjecture, which applies for long distance behavior. Here we are asking whether the force on a charged particle near the black hole horizon is repulsive or not. Okay. Now, the first thing you notice is since we are considering extremal black hole, at the horizon itself, the force is guaranteed to be 0. So this is the same particle in the background of a black hole. It depends on the metric factor F. So for extremal black hole, everything vanishes. So the force experienced by a particle precisely on the horizon is equal to 0. But you could ask, what about near the horizon, slightly bigger than the horizon radius? And that turned into a condition that this force, the first derivative must be positive. And when you work it out, it's exactly giving you this Stringer bound. So an alternative way to state the weak gravity conjecture in AdS is that the particle near the black hole horizon should experience a repulsive force. You don't need the force to be repulsive everywhere, but at least the particle has to be able to escape from the black hole. Now, we also see that the Stringer effect has a spatial extent of the order of the Compton wavelength from the black hole horizon. And when the Compton wavelength is large, comparable to the size of the black hole, you have, instead of a Stringer suppressed effect, unsuppressed charge condensation. And so this suggests perhaps there's a relation between our Stringer bound and the near horizon BF bound, which signals the classical instability in the near horizon AdS2 region via charge condensate. So for AdS, in 4 dimensions, the near horizon geometry is AdS2 cross S2. For a charged scalar field, the BF bound in the AdS2 region take this form. And you can work out what that means. It turns into an expression that looks almost the same as the Stringer bound that I showed you with this additional term here, okay? And so this additional term can be understood as the corrections due to the wave nature of the state. So the difference between the BF bound and the Stringer effect is only relevant when you're looking at a state that is light compared with the AdS scale. So if the Compton wavelength is small compared with the AdS length, this effect is negligible. And so the 3 conditions that I stated agree with each other. Yeah.
Conceptually, there's a difference. Isn't there, like this thing here? So previously you were saying you need one state that charge to mass ratio.
Yeah.
Yeah. But here you would say that all charge states, that all charge fields should have a U-squared theory that in order to not gross compare.
Right. So so I think the charge condensate can also have different value of the charges, right? So in fact,
there's no condensation whatsoever. You just have a black hole.
Yeah.
Be saying that all of these, all those fields obey that bound.
Yeah. Right. So I think maybe this is answering your question. So some time ago, Horowitz and collaborators studied the weak gravity conjecture in light of the cosmic censorship conjecture. What they did was to look at the charge condensate. And then they find that if the charge condensate satisfies something like the weak gravity bound, charge to mass ratio bigger than some value, then this condensate solutions would prevent a naked singularity to form. Okay. So here we are looking at something more on the particle limit. So what I try to bring up is that these additional corrections will be irrelevant for the particle version. But in both cases, it's the same spirit. You have either a charge condensate or a particle satisfy the super extremal condition, satisfy this weak gravity bound to prevent naked singularity to form. Okay. But I hope that this would be more clear to your questions. If I miss that, we should talk afterwards. So let me come back to the apparent contradictions between the weak gravity bound and the BPS bound. Okay. So if you take the wave version of if you take the near horizon BF bound as the weak gravity conjecture in AdS, then that condition applies to states that are even light compared with the AdS scale. Okay. So then there is an apparent contradiction I mentioned earlier with the BPS bound, because one tells you that charge is smaller than the mass, and the other is the charge to mass ratio has to be bigger than something bigger than 1. And there is, to our knowledge, no apparent contradictions because of the subtle issue with the notion of mass in AdS. So if you're looking at large classical objects like supergravity solutions, then what appears in the BPS bounds should be identified with the ADM mass. And so indeed, in that case, the charge to mass ratio is smaller than 1. However, if you are looking for very light states, you just need some states that is light enough to be in the wave region. And for such light states, what appears in the BPS bound should be the energy, which is associated with the conformal dimensions of the dual CFT. And so there's a relation between the conformal dimension and the mass, in general d dimension. It also depends on the spin of the particles. And since here we're considering scalar fields, this is how the relations of mass and conformal dimension reads. And you can check that if the BPS bound is on the conformal dimension rather than the mass, there is a window such that the BPS states could satisfy the weak gravity bound. Okay? So that would be a prediction. If you take this as a prediction for holography, then there must be a dimension-dependent window of conformal dimension in the CFT that is lying within this window. Okay, so it's also natural to ask how our results generalize to multiple U1s, and it's a simple exercise. So if the condition for black hole decay is really the repulsive force conditions between the extremal black hole and the particle near the horizon, you can check that this generalizes to bound on the dot product of the charge vectors. And if the weak gravity conjecture is the quantum gravity criterion that any extremal black hole should be able to decay, this implies that the convex hulls generated by the charge to mass vectors of the states in the theory should contain a sphere with a modified radius. So instead of 1 previously in flat space, there's now a modified radius depending on the size of the black hole. And besides the change in the radius for the weak gravity bound, the states that lead to black hole decay only lies at the vertices of the convex hull. Whereas previously I gave you this argument about how the decay happened into its constituents. It could be any states within the convex hull. Here, the statement would be that only the states sitting at the vertex of the convex hulls are responsible for the black hole decay. And so let me summarize. So the weak gravity conjecture in its many forms has wide-ranging applications to particle physics and cosmology, and has been tested extensively in explicit compactifications of string theory, but mostly for asymptotically flat space. And since the conjecture has mostly been formulated and tested in asymptotically flat space, we want to study black hole decay in both flat and AdS space by calculating the string array in the full black hole geometry. So our findings suggest a weak gravity conjecture that can be stated in 3 different ways: stringer effect non-vanishing, repulsive force near the horizon, and near horizon BF bound. And so there are many interesting questions for the future. For instance, how does this conjecture get modified in the presence of additional scalars? Since black hole solutions in string theory, especially BPS ones, come with whole tons of additional scalar fields, we would like to know how this gets modified. Is there a Tower weak gravity conjecture in AdS? We do not know, and we're working on it as I speak. And besides black hole arguments, much of the evidence for the swarmland came from checking them against string theory constructions. So you may ask what AdS compactification of string theory can be used to test our conjecture. Now, this may be tough because AdS compactifications typically involve Raman-Raman flux, which hinder a complete string theory description. We work usually in the limit of supergravity. An exception is AdS3, which can be obtained with just NS flux. But then you may argue that lower dimensional gravity may not be behaving the same way as 4-dimensional and higher dimensional gravity. And so there is a set of AdS vacuum constructed by DGKT, DeBoeuf, Gilviet, Catrou, and Taylor. Okay? And so they consider flux compactifications in type 2A. And just by turning on fluxes without instantaneous effects, you get a family of AdS vacuum with scale separation. You could, in principle, try to test whether the conjectures that I stated is satisfied in those constructions. But then there are also doubts whether DGKT itself is in the swarmland. because there's a conjecture that scale-separated vacuum do not exist in quantum gravity. So there are a lot of questions, and I don't have the answers, but hopefully some of you would solve the problems for us. Okay, so thank you for your attention.
Thanks for the very nice talk. Are there any further questions?
It's a quite obvious question. So when you consider some holographic CFT, you can translate everything in the CFT language.
Yeah.
So suppose that there is some CFT violating the Schwinger bound you suggest. What would go wrong in on the CFT side?
So here we are doing things with very minimal content, right? So we have only gravity and U1 field and charged particles. So it could be that the assumption is not sound, because in the CFD, there are a lot of operators with different spins. They could be already operators that are not accounted for in the gravity solutions. So I don't think it would be an immediate, I mean, I think I would like to know how this get modified in the presence of this additional bells and whistles before coming to the conclusion that holography is wrong or the AdS condition that I wrote down is wrong.
Other questions? I myself have a small question. So when you were briefly discussing this convex Hall condition in the AdS, I didn't get why was it only for the vertices that you had to?
So, so you are looking for a particle that leads to the non-vanishing of the string rate. So you can draw the convex hull, and only when you have particles lying at the vertices do you have the projection in the directions of the in their charge directions to lead to the decay. So you don't need everything inside the convex hull to be accounted for in the decay process. You just need to find one particle.
But not in the flat space.
Not in flat space. In flat space, the argument I gave was more like a kinematic argument, and it doesn't tell us the dynamical process in which the decay occurs. So if you actually follow the Stringer process, the particle that leads to the decay does not fill out the entire convex hull. It's only the vertices.
Okay. Okay. Thanks.